Hello viewers, welcome back to video tutorial on AIOS. In this video, we'll be talking about model splitting. This is the part 2 of a model splitting video using native libraries. In part 1 video, we were showing the native library where we took transformers and torch distributed. But in this video, we'll be walking through with the VLLM as inferencing and torch distributed for splitting the model across nodes. And here we are calling native libraries, and in this native libraries we'll be doing serving by AIOS, and inferencing will be done by the libraries. Whereas we have one other video where model splitting was done using VLLM itself, where VLLM was doing inference as well as serving. So in this video, the inference is done by the VLLM. Torch distributed is also used as a backend for communication across the ranks, and serving is done by AIOS. So we have already explained all these concepts, like what is model, what all different strategies present in the model parallelism, like tensor parallelism, pipeline parallelism, and FSTP, fully shared data parallelism, and all. And also we have explained the concept of rank 0. I mean, what is ranks, local ranks, world size, and all. Please, before coming to this video, I request you to check the part 1 video. Will be with this heading. So all the Jupyter notebooks are shared in our GitHub, so you can check it. So this is the part 1 where model splitting was done using the PyTorch and transformers and PyTorch, so torch distributed. And here in the second video, we are doing the with VLLM and torch distributed. So and also the folder structures, right? So you can see here part 1 with VLLM torch distribution, and part 2 is where using VLLM for both inferencing and serving. So we'll talk about this part 1 and part 1 VLLM torch distributed. I have opened it here. So what is the difference here? So the between both the folders, there is no difference between the blocks folder. The codes will remain same only. So only the difference is the split SDK and VLLM SDK. So let me go into the split SDK. Let me go inside the VLLM SDK. So here there is a AIOS transformer code. So the main files are there in the AIOS transformers only. So there is a sdk.py and APIs. APIs is basically to host the APIs. If it is a rank 0, it will host some APIs, and if it is rank other ranks, it will do something else. So this is from the first part of the video, and there is a sdk.py where it is doing there is one important function, the save all ranks. So for this function, we were passing a function to call and certain arguments. So that was taking care of calling across the ranks. So what needs to be done, like before doing the inference, you have to send certain data to each and every rank. So if you send that function, what the function is basically like synchronizing the data we have here, like dist broadcast. If you send that function to if you send that callable function to the save all ranks, that used to send all the data to the all the ranks available in the split model split. So this was the function, main function, and using that function only we were trying to do inferences in distributed way, where at the end the distributed function is also was called using the save all ranks only. So this was with respect to the part 1, whereas in our part 2, so let me just go to the part 2 API section. So similar to the part 1, here also we are doing same thing. If it is a rank 0, we are trying to serve a the app. If it is not rank 0, any other ranks, then we were doing some operation. So that operation is basically waiting for a call and things like that. So I'll just go inside. Let me just first explain the apis.py. So if it is a rank 0, I am exposing some functions here like generate and health and shutdown. So generate is the main function which we used to call within a /generate function. Here basically the main function that is being called is either distributed generate. So here you can see, right? So distributed generate is the function, and if you want to shut down all the ranks, right? So I used to call a stop worker. So and if it is not rank 0, then if it is some other ranks, I will call a run worker forever. So let me go to the sdk.py. So here is my distributed inference SDK. So in this you can see, right, I'm initializing with NCCL if available. If not, glue is the backend. And by default, when we are initializing with NCCL, right, so it will take a default of 10 minutes of a timeout. So more than that, if any communication is there, right, so it will discard, meaning it will close the connections. So in order to give a bigger timeout, so I have set like time delta equal to 30 days. So this connections, whatever the connection within the ranks will be there, right, it will be waiting there for 30 days. So you can increase this more as well. So if it is glue, I guess it is 1 hour or something like that is a default value for a timeout. So for NCCL, default timeout is 10 minutes, but I am changing that to 30 days. So later on, the important things are like you are creating a model here using LLM function provided by the VLLM library. So I'm using LLM and sampling params, two important functions. So in the LLM section, so I'm giving the model name, how many tensor parallel size required, pipeline parallel size required, and distributed executor backend. So this since VLM has a tight tight integration with Ray, by default it will take a Ray. If not, you can do a MP as well. So MP is for multiprocessing. If you are doing within the same GPU same node, you can use the MP as well. So right now I'm giving an external launcher. So what it means is I am depending on some other launcher than the provided by VLM itself, which is Ray or MP. So you have to give this external launcher, and what is the max model length it takes, a random seed. Then this gen config is a generic configuration, like it's a dictionary here. So I'm initializing with some value. Later on with this function, right, so I can update any, like user sends any other parameters or updated parameters, updated values of this. I'll be doing a update operations here. So distribute generate is my main function. As you can see here, as soon as a generate function is called, distribute generate function is called, right. So let us go into the what that function does. So basically I'm creating the config here, like basically those configs are from this whatever the default configs, and also the override, like if you have sent any new configurations, right, so that will be merged here in the CFG. So there is one list I am creating here, so call it as message list, which has 3 items here: gen, prompt, and a CFG. Prompt is what user sends the strings or their query, and CFG is this particular dictionary, and this is a string with a gen. So this is only for rank 0. If it is not rank 0, right, so then it will be none, none, none. So right now this message will be broadcasted to all the ranks using this particular function dist. Dist is a PyTorch distributed library. So using that dist broadcast object list. So this function I'm calling, and I'm passing this message. So as you can understand by the name, right, so this broadcast object list can send a list of Python list it can send. So that's why we have to give a list, and we should make sure that the whatever the content you are sending here is a pickable, meaning you cannot send items like date time object or all. You cannot send it. So it has to be an Python pickable objects should be present in the list, and that list I am broadcasting to all the ranks. So the source rank is 0. So right now it is sent, and all the ranks will receive this particular data. Like say this is for a rank 0, right? So in the rank 0, again I'm getting what is a prompt message and configuration. So I need to for VLLM to create the this configuration files, right, you need to convert it to something known as sampling param. So that's why this function is called here, and I'm passing that CFG. So what it does is basically simply create an object of sampling param class by sending all the keywords here, like the KW args here. So that sampling params variable is created here, known as SP here, and then I'm calling a self LLM generate. So right now this knows that there is an runner distributed, so external launcher is available, which is a torch distribute library is being used there. So it will do a inference with the sampling parameters and prompt that you have here. So at the end you have a barrier. Basically it is for a synchronization across all the ranks. So once all the ranks are synchronized, so I'm doing some operation here to try to extract the output of it, and then I'll be returning the output. So if it is not rank 0, I'll simply return. So this is, but this code is mainly runs for the rank 0 guy. So now let us see for a non-rank 0. So any other ranks which are waiting for the, which are not rank 0, basically they will execute this function. So it is in a while loop. So here I'm initializing this message with none, 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 because I want message from rank 0 to be sent. That's what this broadcast list is doing. So right now I'm initializing with none, and I'm doing a dist broadcast object list message from source 0. So from there I'm taking the message 0. That value is something known as command. That's what is gen is. So that command I am trying to take it. I'm checking whether that command is stop or gen. If it is gen, I'll be going for a generate operation. If it is not a gen, or if it is a stop or something like that, right? So then I'll be doing a break operation, because I'll come out of this loop. And if when I come out of the loop, all ranks are come out of this loop, and they will be away from the this function. So they'll be out of this function. So right now, yeah, if it is stop, I'll be doing a synchronization operation, because I need all the ranks to be synchronized, and then only break the loop here. And if it is command is gen, then I'll be doing again sampling parameters, and I'll call a LLM generate. So the VLLM object will take care of synchronizing within the ranks, and create a tensor parallelism and provide you the output. So that will take care. So you have to provide a dist barrier here, so that all the ranks are synchronized. So if it is not gen, so you are simply doing a dist barrier here. So this is a simple function. It's not that complex compared to the our part 1 video. So where in the part 1 we were doing a lot of things from our side, where sending the data, say, doing the inferences, everything we were only doing it. But here few things is done by the VLLM itself, like inferencing is done by the VLLM, synchronization between the ranks are taken care by the VLLM. So only thing is we are passing the object list only from our side. So this is the simple function for available as sdk.py in AIOS transformers. So that is so that's it about this particular code. So you can basically build a similar approach you can take, like to build the Docker. So you have to go to VLLM SDK and build the Docker. You can build it, and then you can push the Docker to your centralized registry, and then you need to run the inference. You need to create the splits container. So the splits container is right now we have an API known as splits/create. So that will take certain parameters. You need to provide rank wise, like say if you want to run a 4 rank, right? So then you need to provide a 4 dictionaries here, and what the dictionary content is, I'll explain. So rank, so you need to, since it's a rank 4, you need to provide rank 0 goes to what node, and what interfaces it uses, and which is the GPU it has to take, and what is the cluster ID, and CUDA visible devices, things like that. So for rank 1, so basically I'll be putting both the ranks in same GPU. That's why I'll give GPU node 2 here, and I'll call this as rank 0 and rank 1. For rank 1, I'm giving NVIDIA visible devices as 0 and 1, but the CUDA visible devices 1. In that, though the two GPUs are volume mounted, when the program has to run, it has to take only the first GPU. Here it is only the 0th GPU. This is for rank 0 and rank 1, whereas rank 2 and rank 3, I will be splitting across again one more node known as GPU node 7, which has two A100 cards. Both this GPU node 2 also has two A100 cards, and GPU node 7 also has two A100 cards. So I will be splitting rank 2 and rank 3 in GPU node 7. So this is for rank 4. So you need to provide the model name here, and you need to provide HF token. Don't forget that, because Gemma model, or the model that we have taken for our demo, right? So they are a gated model. You require a HF token from Hugging Face, and you need to provide this VLM runner container that you created here. So you have built, whenever you build the Docker, right, VLM runner container will be created. So that Docker image you need to provide here, and master port and max model length also you need to provide, or else you might get into a error. So now once this if you understood this, similar to that, you have a 2 node section. I mean for 2 rank section also I have given this structure. So for the 2 rank structure, I'm just using GPU node 2 and GPU node 7, and I'm using only the 0th GPU in it, in the both the GPUs. So this way, I mean, if you run this, right? So splits model will be created. So I'll just show you that. So first you need to run this particular cell, because it has a lot of env variables that will be used in the subsequent sections. So let me run for a two node section, sorry, rank 2 section. So let me just run it. Yes, deployment is created. The name is something wrong, so you don't have to worry about this naming. So let me just to see the pods coming up, let me just go to, yes, so there is one pod is getting created. So let us log this particular log, this particular pod. This the namespace is splits, and only one container is there in that. So let me just log it. So this might try to pull the the container image, or it might pull the model as well. So it might take some time. So if the models are already available, so it will quickly load. But we have seen that when you in this particular section, right, where VLLM itself will take so much time in loading the model when you are running VLM as a not a model splitting. So but since your model splitting is there and ranks are there, right, so they will take more and more time. So in our observation, it is like 8 to 10 minutes around it will take just to create the containers ready for serving inferences. So until that we need to wait it. There is no other options from for us right now. The container is still creating, so let us wait. So 90 seconds are gone now. So container the rank 1 is yet to create, but the rank 0 is created. Let me try checking the log of rank 0. Finally the model has loaded. So let me just check the time of it, how much time it took. So it took almost 8 minutes 23 seconds to load the model. So if you check the logs, right, so you will see what all operations the VLM is doing. So it is doing it loads the model, and then it will try to take as much as KV cache as possible. So to control the KV cache, you have to use certain parameters, but right now not given to the model. So it will take as much as RAM, around 90% by default it will take. That's how the VLM is configured. So once the model is ready, so since it's a rank 0 container, so it will host a app flask app. So it is exposing a endpoint. So if you check same thing for a rank 1, so that will be in a while loop. It will be waiting for any activations from coming from the rank 0. So it is not hosting anything, so it is just waiting. So let's go to the rank 0. So yeah, right now the model is available, model is ready for inferencing. So let's go back to the Jupyter. So now the model splits are ready, but we want something known as proxy block. Why proxy block? Proxy block will do the inferencing with the splitted model, and the proxy block will communicate with the splitted model using the service IPs. So that's why we don't have to create a cluster IP or a node port for this particular service. So it will take care of speaking via the service IP only. And what any sort of a logic you want to build, like a chat history kind of thing, right? So then you can use the a proxy block. So proxy block will simply pass on whatever the communication you are doing to the splits, and once the split is returns back the result, the proxy block will send the result back to the caller. But in between there is something known as inference server that we have already explained what is inference server, but I'll again try to give a walkthrough. So right now the splits are created, and you need to create the proxy block. So the block That's what the this code is all about. This block code is there, right? So that's what is a proxy block. So you can build that particular block docker, and you push the docker, uh, push the docker to the registry, and you have to register the component. If the register might already be if you have run the first video, right? So registration is already done. I will not do that. So then you have to deploy the proxy block. So once the proxy block is deployed, it will be in a blocks so proxy block will run in the blocks namespace, because any block that we create will by default will go to the blocks namespace. I can just log this, and there are two containers in it. So the first container I need is a instance will give you a proper log for your code for a proxy block. So that is also loaded, because it doesn't have any models or anything. It will quickly load. So yeah, only the VLM will take time for loading. So now the proxy block is loaded, and splits is also loaded. VLM splits are also loaded. You require a inferencing server. What this inference server does is that acts as like, you will be talking to the inference server. Inference server, in contrast, will talk to the block, and block will talk to the splits, and then communication flows back to the user, like from splits to block to inference server, and inference server to us. So this inference server we can use to speak to any block we have in the the cluster. So at least one inference server is required if you want to do direct interface to the any of the block in the cluster. So uh, first create the inference server. So YAML is provided. You just have to create the inference server in the cluster. If one inference server is already created, don't create again this inference server. So you can create the inference server with a different namings or things like that, so that you have to take care. So yeah, right now in my case, inference server is already created. I will not create it again. Now for inferencing the block. So v1 infer is what we need to use the endpoint, and this is the inference server's this is the inference server's endpoint, and this is the port. So right now I have to give PyTorch block 3, which is nothing but this particular block whichever is created, right? So that is nothing but PyTorch block. The name I have not modified from the previous thing, so the name is carried forward. So you need to change the sequence number whenever you want to do new inferences. And let me do it for Python for time being, and let me do the inference. So we need to wait for like some 20-30 seconds, depend on the model. So this model might come within some 25-30 seconds. Different model will provide you a different kind of time variations, response times. So I'm generating a max token of 512, some top k, some dummy values of top k, and temperature, all those things are sent. This is my default. I'm asking a message here. So basically this content will go to the block, and block will convert whatever the data here, right? So it will convert accordingly what the splits API, that generate API is there, right? So the generate API, so it requires a prompt as a key, and it requires a maybe a the generation config, data dot items, whatever is there, right? Whatever other parameters are there, so that will be a generation config. So that we need to send here. So that is taken care by the blocks code. So whatever you are sending from, yeah, whatever you are sending here, this will get converted by the blocks code, and blocks code will properly format the data for this API to work. So now we have got the response around like 25-26 seconds. So similarly you can try for any other message, maybe let's say Java. So let me change this to 30. So I just want to show you GPU utility in between. So this is one node, and this is the second node. So as you can see, the GPU utility 8990 is going on, and it has taken almost 75 GB of RAM. So why? It's because of VLM, or else by default this model would have taken somewhere around 20-30 GBs maybe in each GPUs. So the data I'll show you in some time. Yes, we have got again the result in 23 seconds. So this is how you will be doing a splitting of model using VLLM and torch distributed. Again, just to reiterate, we have used AIOS doing serving, and the inference is done by the VLLM library. In the part 1 also we were doing serving, and inference was done by the transformer library. So at that time the transformer library was not that, we have not fine-tuned the transformer library to give a better throughput, so it could have taken more time for giving the inference result. I'll show you that. So, and whereas in the part 2 of our video, where it's a completely we call it as third party. Now these all are not third party, we call third party here because the VLM is there, which is doing a inferencing as well as serving. The endpoint will be provided by VLM, and inference is also done by the VLM. So, but whereas here the serving is done by our AIOS, and inference is done by VLM, and torch distribute for distribution task. So that's how you need to, that's how we'll be doing the inferences in with the help of VLM block. And once the inference is done, don't forget to clean up. So I'll clean the model split first, and once the splits are deleted, I'll delete the proxy block. So so this is pretty much about the demo showcase. So let me just show you the comparison results from our previous runs. So this I've already shown you in the in part 1 video. This was shown, and in part 2 video this as well as VLM ray was shown to you. And here this is the 512 tokens, and this one is for a 2048 tokens. But here right now I have done the same benchmark for both the models, Meta Llama 3 70B instruct model as well as the Gemma 227B model. So just to compare here, the third one, which is the current whatever we have run, right, VLM with torch distributed, is here. So you can see that the output is pretty much comparable. Just to give an example, we can completely avoid this because this was giving very less tokens per second, and the time also it was taking 209 seconds or 195 seconds. So here you can see this was for a VLLM from 512, and we can basically compare this and this here. So this was taking 41 seconds to 43 seconds, and it was generating from 499 96 tokens to 512 tokens, though we asked for 512, but Python code would have taken less tokens, and total tokens per second was 12 to 12.3, whereas in this case it was giving like 42 to 52 seconds, and the tokens per second was somewhere around 9.6 to 9.8. So and this was for rank 2 ranks. So, and when we check for 4 ranks, right, so here 63 to 73 seconds it was taking and giving a 7 to 7.5 tokens per second, whereas here it is taking 50 to 61 seconds, where the tokens per second on an average it is giving is 8.37 to 8.66. And as I told, don't forget this numbers, like it took around 7 to 8 minutes or 10 to 11 minutes to just to be splits be available for inferencing. And GPU utility is also pretty much like 94 to 96 in this case, and 91 to 95 for all the 4 GPUs here in this case. So that was for a Llama 70B instruct model, and this is the next 2 row, the 10th row and 11th row is for a Gemma 227B model, where you can see it was taking 20. In the last video we were having some wrong results with us, but we have again re-evaluated and corrected it, and we found that it was taking 23 to 23 seconds for a Gemma 227B model in rank 2 by giving, it was giving tokens around somewhere around 21 to 23, and current versions that we have is giving 18.29 to 20.98 tokens per second, and the time it was taking is 28 to 24. So RAM wise, you can see similar numbers, maybe like 54 GB here because it was rank 2, 2 into 27 GB it was taking, whereas this guy here it is taking 28 GB 2 into 28 GB, because VLM takes some more RAM for a lot of other operations. But by default, VLM will take 90% of the RAM that we have not controlled. Here also we do not control, but this is the last RAM, like 27 GB was the last number that we were seeing in NVIDIA SMI before going to around 70 GB. Because the A100 was having 80 GB, 90% of it is around 72, 73 GB. So before reaching 72 GB, this was the number. So we assume that this is the total RAM usage of that particular model if we have not given, if we have controlled our KV cache size. So this was for rank 2, and for rank 4, it was 13 to 14 tokens per second is what we were getting. 35 second, 37 second, and 38 second for our Python, Java, and C++ query. Whereas in this case, it was around 33 to 34, 32 to 33, 32 to 33, and around 14.9 to 15.7 is the tokens per second, and RAM is being almost similar. So it was 61 and it was 58, 59 GB it was consuming. So yes, this is about comparisons with respect to the third-party VLM with Ray and VLM and torch distributed. So tokens per second remains almost pretty much it remains almost comparable or on par with the VLM Ray. So this was these two models. I mean, if you check any other models, this might vary with respect to the models as well. So yes, so I guess we are reaching to the end of the video. So basically we showed you how to split a large models across multiple nodes using VLM and torch distributed. In part 1 we have shown transformers and torch distributed, and we have also shown you how to create a proxy block, and that proxy block will do the inference to the rank 0 of the splitted version of this model. And then we have shown you the APIs, the AIOS integration with model split API for VLM and torch distributed was shown, and also the inference server. Again, inference server is acting as an the front end for all the communication from the clients, and inference engine which is provided by VLM and torch distributed. So that's it for this video. Thanks for watching. Don't forget to subscribe our video channel. Thank you.